So on problem 17, it says the Maclaurin series for ln of 1 over 1 minus x is given by this, x to the n over n, with this interval of convergence. So they are including -1, but not +1. Find the Maclaurin series for ln of 1 over 1 plus 3 to the x, or 3x. So, and determine the interval of convergence. So we can build this because we have the series for 1 over 1 minus x inside of the natural log. So first of all, I'm going to write this as 1 over 1 minus -3 to the x, because it's not that we're subbing in a 3x, it's that we're subbing in a -3x to get that expression. So that's kind of the trick on this. So write the series doesn't mean we have to expand out the first 4 terms. It just means go ahead and sub that into the series and you can simplify it as you're doing interval of convergence. So we're going from 1 to infinity. Instead of x to the n, it's the quantity -3x to the n over n. Again, you can simplify that if you want to, or you could leave it. Determine the interval of convergence. So it's not that it's just the endpoints that are going to change, because we have this 3x expression that's going to be affected. So I'm just going to pull out the negative, just so I don't accidentally put that in when I'm doing ratio tests. So we can separate out this -1 to the n, and then make it times 3x to the n over n. So here's my Maclaurin series. Determine the interval of convergence would mean use the ratio test. So the limit as n approaches infinity of the absolute value, so ignore the alternating piece, of 3x to the n plus 1 over n plus 1 times the reciprocal of the nth term, so n over 3x to the n. I'm going to write what that is simplified before I take the limit. So the n over n plus 1 will still be here. We should have 3x to the first left when we divide these out. And so that's going to give us the absolute value of 3x. This converges by the ratio test if 3x stays between -1 and 1. We're finding the interval of convergence, so divide by 3. And then remember to test the endpoints. You do need to show what you're testing. So when x equals -1/3, the series would be from 1 to infinity. So if we plug in -1/3 into -3x to the n, we would just get 1 to the n over n. So that's a divergent harmonic series. So we're not including that endpoint. And when we test x equals +1/3, because we're plugging in a -3x times 1/3, we would still get a -1 to the n over n. So that's the alternating harmonic series. So this converges by alternating series test. So that means that the interval of convergence is not including -1/3, but including the endpoint +1/3. All right, part B says find the value of the sum from 1 to infinity of -1 to the n over n. So what does this add up to? Now remember, we just figured out that when we plug in -1 to the n, that's our value that, or when we plug in 1/3, we get this -1 to the n over n, which converges. So when we plug in -1, we're actually plugging into the function that corresponds to that. So take a look at this. -1 over n to the n matches with the original ln of 1 over 1 minus x. And we know that when we plug in -1, this series converges to exactly this function value. So for part B, I'm going to say the series from 1 to infinity of -1 to the n over n is equal to f of -1. They didn't actually call this f of x, so I better specify. That equals the natural log of 1 over 1 minus -1, which is the natural log of 1/2. We would leave it at that. So the function value at -1 matches the series value exactly because we're still within the interval of convergence. Part C says give a value of P such that this series converges, so the alternating series converges, but the non-alternating diverges. Give reasons why your value of P is correct. So give reasons can just be show your work, and make sure you cite the correct P series test. These would both be a P series test here and then alternating. So let's start with the divergent term because P can be anything except for a negative, I guess, for the first part, which we'll address in a minute. But I think it's better to start on the divergent part. So, all right, so let's write down that series. The series from 1 to infinity of 1 over n to the 2p diverges by P series test if, remember the rule, harmonic series and then anything with a fraction. So if this 2p comes out to be anything less than or equal to 1, then you're going to get something that diverges. And that would include negative values because if you have a negative exponent down here, then this is going to diverge by the nth term test as well. So to satisfy this condition, p should be anything less than or equal to 1/2. But we also have to pay attention to the alternating series. So we need the alternating series to converge. And this would be true as long as, like I said, if you get a negative exponent, you're going to get -1 to the n times some expression, and that's not going to converge. It'll diverge by the nth term test. So I'm going to say converges by alternating series test if 2p can remain greater than 0. It can't be equal to 0 because then you get -1 to the n over 1, so that's no good either. So that's just as long as p is greater than 0. And so if we put these together, we need p to remain between 0 and 1/2, and we include the 1/2. For the second scenario, last scenario, I should say, this says give a value of p such that the non-alternating p series diverges, but when we put in 1 over n to the 2p, that converges. So neither of these are alternating, so let's just take them in order. So the first series was the sum from 1 to infinity of a non-alternating, right? Yeah, 1 over n to the p. So this one needs to diverge. So this will diverge by P series test if P is less than or equal to 1, right? Harmonic or anything with a fraction. And then our second series was from 1 to infinity of 1 over n to the 2p. And we need that to converge. So that would converges by P series test if 2p is greater than 1. And that would mean that p is greater than 1/2. Can't be equal to 1/2 because then you get harmonic. So in this case, p should be anything between 1/2 and 1, including the 1, but not including the 1/2.